Yeah, recorded is rolling. It is Tuesday, August 26th. All right, so for context, we are on short time. We have about 15 minutes. Let's see what we're gonna bring you guys here. So have this car and incline lab. Finish off the graphs with you guys. Don't worry about anything that says AP. Just ignore that. All right. You guys know there's a quiz coming up on Friday. Anything we've been doing in class. All right, so context there. All right, so you guys have this lab. You guys were sending Hot Wheels cars down the incline. We're trying to figure out what equation or equations could govern the motion of the car. I split you guys up into these experimental groups. And yesterday we put together the graphs for mass versus time, distance versus time, speed versus time. And here's a recap. So mass versus time looks like this. You guys have, well, there was one team, one or two teams. You guys had lots of different mass cars, and it came out to be the same time over and over and over again. What does that tell you is the relationship between mass and time? Yeah, no relationship. Yeah. So mass is not going to show up in the equations. So it turns out it doesn't matter how massive the car is, the equations will be the same for a light car as they would be for a heavy car. Right. Then you guys had displacement versus time. So how far does the car roll as a function of time? Now, obviously, the more time it roll, the further it's going to roll. But that turned out to be what shape is that right there? A parabola, or it looks like a parabola. We were suspecting parabola. We could confirm that by if you square the time axis. Now this is a little tricky. I don't know this. Have you guys ever done this linearization before, or is this entirely new?
No.
No. Okay. Yeah. Right. Yeah. Right. So it turns out if you square the time axis, then all these points line up in a straight line. Okay. And the advantage is that you can very quickly whip off the slope. And okay, this ended up being the slope for well one of my classes. Okay. So you say, okay, x is proportional to t squared. Let's say the distance the car rolls is proportional to time squared. Okay. This equation that I circled here also describes this parabola. So on an x versus t axis looks like a parabola. X versus t squared looks like a straight line, but it's the same information. Okay. X got that, got that, got that. And then this is the last one we did, and then the bell rang. So velocity versus time. Now the fact that v versus t comes out to a straight line. Remember, this is the final. So the speed of the car at the bottom of the incline is going through the speed gate means that, guys, if the car was rolling for twice the amount of time, would it pick up to twice the speed? Yeah, that's exactly what that means. All right, that's a direct relationship. All right, so now we're moving on to next one. Couple. All right, we got to do these ones with the hearts. Now, hearts is if you had speed as a function of distance, not speed as a function of time. That's obviously this one right here. Okay, speed is a function of distance. Okay, you guys ready to do that? Now, the further the car rolls, you think it's going faster. Okay. Now, here's where we're going to do a little shortcut because if we get the data from you guys, I know you guys got some good data, but I'm just going to have you guys do this because we're on a shortened class with the storm and lightning and whatnot. So, for velocity versus distance, go ahead and make a curve that kind of bends down like that. And again, if I got the data from you guys, to do the same thing. Okay. Yeah, just go ahead and make the. What shape do you think that is right there? Does that look like here? There's some candidates. Which one does that basically look like?
A root.
Yeah, probably a square root looking right here, right? You guys think it's square root? Okay. Just go ahead and whip off a square root graph. Okay. Now, if it is a square root, that means I should be able to square the speeds to a v squared versus x, so like velocity squared versus x, and that should linearize, right? And if it does, then that would confirm that this is a square root. And furthermore, we could get the slope and make an equation that would also describe this graph. Right? Right, so you guys just made a square root looking graph. Okay. And I have variable, or no, sorry, variable units. I think I wrote this in for you anyway. Okay. So then what happens if you do v squared versus x? This was one of my earlier classes. You guys, I'm sure the data would be the same. Right. So notice I squared the velocities, and as a function of x, does that stay the same? Okay. Yeah, this did in fact come out to a straight line. Then I could pick 2 points on the line, find the slope. I got the slope, so I can come up with an exact equation. So v squared is proportional to x. Okay? And if you want to make that an exact equation, then, well, that's where the slope comes in, and you get an exact slope number there. Here's that too. Okay? So I could say that the square of the speed, like the final speed, that's what the f is for, final, like at the end of the incline, is proportional to how far the car is rolled. Right? There's a proportionality symbol. Yeah, if you want equals, you need that number 119 centimeters per second squared. Okay. Or, guys, can you apply some algebra? Yeah, go ahead.
Have you put the other graph on?
Yeah, guys, all I want you to do is draw the basic shape. So for v versus x, just whip off a square root, done. That's it. Okay. One smooth motion. Okay. We're doing a shortcut here. Okay. And for v squared versus x, just go ahead and just whip off a straight line. Okay. And that's all I'm looking for. If you do that, we're on short time here. Okay. Can I play algebra rules and take the square root of both sides? Can I say this? Can I say that the speed ends up being proportional to the square root of how far it rolls? Right. And here's what that could mean. Is for example, suppose you let your car roll 9 times the distance. So let it roll 1 meter, and then let it roll 9 meters. Isn't that 9 times the distance? Guys, 9 times the distance is going to correspond to how many times the speed? 3 times. Yeah, because isn't the square root of a factor of 9 a factor of 3? Square root of 9 is 3. Right, guess it? So we've got some proportionalities going on. Right. Now, what I'd like to do, ideally, is build.
As an interruption, teacher. Despite our transition, we are still in a shelter in place due to inclement weather. We are not out of the woods on the lightning yet. I did want you to get to 7, so please keep students with you in class until further notice.
All right. So guys, if you collect all 6 graphs, you guys have all 6 graphs. You can actually derive these equations just from that. Like it's all laying around just to put together. So I'm going to do that with you guys right here. So let's do this. Get some variables on the to define. Normally I call them tax VV just as a device. So we got time. T stands for time, and time is going to be measured in seconds. You guys know units are also important in class. So variables have units. I'm going to skip this A and come back to that. X is going to stand for a displacement. How far has something moved? And that could be in meters. It could also be centimeters. That's not good. Okay. What do you guys think the V stands for? Velocity. And the little subscript not means initial. So initial velocity. And then V sub F is going to be your final velocity. Okay, so if the velocity is changing, say if it's speeding up or slowing down for that matter, then at the beginning and the end of the interval, you'll have different instantaneous velocity values. And in this class, it's going to be in meters per second because we're using the SI system, the metric system. In your car, you might call that miles per hour, but you guys see it's the same concept, right? Distance compared to time, meters per second, miles per hour. Okay, right. And if the velocity is changing, well, it's got to be changing at some rate. If you ease on the gas pedal and speed up slowly versus you slam on it, speed up fast, you can definitely feel that, right? But if you slam on brake, you can feel that in a car. So you can feel, what do you think A stands for? Acceleration. Okay. And this is a rate change in velocity. So it's like how fast is your velocity changes. It's going to be meters per second per passing second. I'm going to call it meters per second squared as a unit. That's how we can quantify this. Okay. Okay. So with those on the board, so we're working with those variables, so it's these 5 variables. Okay. I'm going to set up a definition for acceleration. So acceleration, and then out of this, think that your first domino that all these other, we're working towards deriving all 3 of these one at a time here. Okay. So acceleration equals the rate change in velocity. Okay. So how quickly is your velocity changing? Right? Are you speeding up slowly, or are you speeding up real fast? Or are you coming to a break for that matter? That would be like a negative acceleration. Okay. Okay. Now let's turn this into like an equation form. Acceleration equals. Okay. See if you guys can figure this out. Apply some critical thinking here. I set up a giant fraction bar. You guys see my giant fraction bar? When I say rate change in velocity, how can you sort of put that in math terms? Rate change in velocity. What do you think that is? How about change in velocity per time interval? Change in velocity per change in time? You guys know the triangle delta. That's a change in, right? Right. So change in velocity per change in time. And the word acceleration is going to shorten to A for acceleration. Okay. Guys, change in velocity. Could that be your final velocity minus your initial velocity? Like that? And then for delta t, I'll just say t. Sometimes I'll use that interchangeably. So delta t could be a time interval or just top t. Okay. Is that okay so far? That equation makes sense? So acceleration is the rate that you're changing your velocity. It looks like this in terms of these characters. Okay. Now let's do some algebra here. You guys ready to do some algebra? Okay. Little algebra shuffle. Can you guys solve for VF? So it might be a couple of algebra steps. I want you to have VF equals something. See if you guys can get it before I do. Get VF equals something.
Yeah.
VF equals something. Right. There's no numbers. It's all letters. It's all letters. Okay. Right. So guys, what's the first step?
Times of x.
Yeah, times t. Yeah, so a times t, just cross multiply that t. So a times t equals v final we're solving for minus v initial. And what's the next step? Yeah, add this v naught over. Right. Now while I'm at it, I'm going to swap both sides. You'll see why here real soon. So final velocity equals initial velocity plus acceleration times time. I mean, that would follow, right? Isn't that true? Okay. Now that right there, that right there is this guy. Oh, it's the same thing. Look at that. So the velocity you build up to, the speed you build up to, is the speed that you started at, plus the rate you're changing, how fast you're moving, times however much time you're doing that for. That's it. Then you put it all together. Is that correct? Okay. Now, guys, this is kind of like y equals mx plus b, sort of. Y equals mx plus b. In fact, because it is, and let's break out this graph here. Now, there's a lot going on with this graph, okay? But let's just start with the y equals mx plus b form. All right, so here's velocity as a function of time. Suppose you have your car speeding up. Okay. Actually, you know what? That actually is a graph you guys did. That's the last one we did yesterday. Isn't that this velocity versus time? The last graph from yesterday, right? The only difference is your car started from rest, right? You let your car go, so it started at 0. Okay? But maybe in this case, what if you give the car a little push? Give it a push. Wouldn't it have an initial velocity? Right? But then everything else would just follow. So the slope of the line doesn't change. The slope of the line, the acceleration has to do with what gravity field it's in and what the incline angle is, right? Okay. But it can have initial velocity, just slide the whole thing up. Isn't that true? Right? Now, remember how I just gave you guys the notes. I said acceleration is the rate change in velocity, right? That shows up on this graph as, guys, what property of this graph is acceleration? The slope. You guys see slope? Right? I mean, isn't that the same thing? What we were just talking about? Okay. It works also in terms of units. It's a real close attention. I want to show you a trick that's really useful for all different kind of graphs in this class. Okay? You guys see how the vertical axis is in meters per second? Meters per second. And the horizontal axis is in seconds, right? Right? And slope, isn't slope rise over run? As in you could divide how much rise over how much run. Now what if you do that with the units? Because what is meters per second per second? Meters per second squared, which describes an acceleration. So if you didn't know, well, now you would. You say, well, I know the slope would have units for acceleration. Oh, so the slope represents the acceleration. Is that true? Right? How about this? All right, let's look at a different property. Okay, let's make this real simple to start off with. Suppose you were going constant velocity. You guys see this dashed line? Suppose that was the graph, just for a moment. Okay? You're going 60 miles an hour, 60 miles an hour, 60 miles an hour, going on 995 towards Jacksonville. 60 miles an hour, right? Just constant velocity. And you do that for like 3 hours. How far have you gone? 180 miles, right? Because the hours would cancel. And oh, do you just do like 60 times 3 and the hours canceled? You got miles, right? Now, in the metric system, we got meters per second and seconds. And watch this, guys. What's meters per second? Oh, in terms of shapes on a graph, wouldn't that be the area of this rectangle? Would be the same calculation you just did, right? You guys, do you see that's the area of the rectangle?
Yeah.
So what if I had the height of the rectangle is some number of meters per second, right here, and the base is some number of seconds, and I multiply that, like base times height per area of a rectangle. Okay, because what unit is that right there? Meters. Oh, which tells you like a displacement, like how far have you gone? You guys got that? Oh, I went 180 miles. Or in this case, like that, so many meters. Sure. Okay. Great. Now, let's do this. Let's go more complicated right here. Okay. Let's say I'm going to draw another V versus T. Let's look at the triangle, because I do see a rectangle down here, but I see a triangle sitting on top of it. I want to make sense of just a triangle bit. So let's just start from rest again. So velocity in meters per second, time in seconds, take along. Right, let's go up to like right here. Right. Let's say for some time t, or if you like, maybe this interval could be some time t, starting from 0. Right, starting. Right. And I know that this slope is a for acceleration. Okay. So what's this final velocity, Vf, that I build up to? So this is v versus t. Okay. The final velocity. Could you guys say that this is here? Well, how do you guys that? Is this a times t? I know we're short on time. Is this a times t right here?
Yeah.
You guys agree with that? Okay. So the area of this rectangle, which represents how far you would have moved in an accelerating situation. Guys, what's the area of a triangle?
1/2 base and height.
Yeah, 1/2 base height, which in this case represents how far it went. Call it x. Okay. So x equals, I got 1/2. The base is some time t. The height is a times t for accelerating. Put that all together. Is that 1/2 at squared? Is that what that is? 1/2 at squared? Okay. Right. Now go back to here. Okay. So a constant velocity situation, cruise control, you're going speed times time. Accelerating, you got 1/2 at squared. Now add those together. Guys, what's that rectangle plus that triangle? What is that?
AT squared.
Oh, it's this guy right here. There's your rectangle. There's the triangle. And there's how far you moved. You guys see how these are clicking together? Okay. Now for this third kinematic formula. You guys notice this last one doesn't mention how much time has passed, right? But the first two do. So do you guys remember substitution from algebra? Substitution?
Yeah.
Turns out, and this is just one way to explain this. If you substitute out the time of one equation in terms of the other, here's what the full proof looks like. Here, I'll leave this here, and then if you need to go home and screenshot this or get a closer look. Right. So I start with these formulas that we derive this, right, and then do some substitution. Bing. At the end, you get this third kinematic formula. Okay. So great. Now what? So next couple of days, we're going to be solving lots of linear motion puzzles. I think I gave you guys a page the other day. Where is it? Well, drive within reach. I'm sure it's one of these around here. Okay, anyway, okay, that's this one. I gave you guys this page the other day. Got some graphs on one side. Got some classic linear motion questions on the other side. Next couple days, we'll be looking at those. Okay. Here's a general rule. You guys remember we have these 5 variables floating around: time, acceleration, displacement, initial velocity, final velocity. Right? If you can identify 3 of these within any question, the other 2 become solvable. So if you know like how much time has passed and how far something went, the acceleration, you can figure out how fast it started, how fast it ends, or something like that, right? Or any of these things, right? All right, so there you go. Yeah, I think we did pretty good right there. Okay, so go ahead, make sure your name's on your lab page. You guys have the table on one side. Okay, you guys have a table of data on one side. You guys have the 6 graphs done on the other side. Right, and yeah, for that to the great Shay, that's a wrap on class.
Until